Thanks for the introduction, Dean. Yeah, good morning, and welcome to the second part of the introduction to quantum numerical linear algebra. And I'll just start with a brief summary of what we had yesterday. That is, yesterday we discussed about basic numerical linear algebra operations. That is, we have some input models on quantum state and on the vector, which is quantum state, and on the matrix, which is block encoding, and also we discuss how to do matrix vector multiplication by just simply applying the block encoding, but you will have some overhead. You will have to some number of repeats in your algorithm. And we discuss how to do the matrix or the vector addition by linear combination of unitaries. And also we discuss several approaches to perform matrix multiplication. And today's tutorial will about we know these basic linear algebra operations, and then we are going to use them to design some numerical linear algebra algorithms. That is, we are just going to we will try to solve linear systems, and also we will try to implement some matrix functions. Okay, so I'll start with the solving the linear systems of equations. But at the very beginning, I will just define what do we mean by solve a linear system problem on a quantum device. Because we start from the classical setting. That is in the classical setting, so actually we are given a matrix, an n by n matrix. So here I just assume it is Hermitian, but it's not a quite, it is not a quite restricted assumption. And I have B is an n-dimensional vector, and then classically we just want to compute A inverse times B. So here, if we have a non-Hermitian matrix, so actually we can consider this dilated system. That is, we have a larger matrix. It is a 2n by 2n dimensional matrix. I put A on this block, and I put A dagger on this block, and then you can see that. So this system is a equivalent linear system. It is equivalent to my original AX equals B, but here we just double the dimension. On a quantum device, so double the dimension is usually not a very big computational overhead because you can just add one more ancilla qubit. Okay, so I will just only consider the Hermitian matrix, and then on the quantum device, so actually by solving this quantum linear system problem, actually we are trying to prepare a epsilon approximation of the quantum state, which is the normalized solution of my exact solution A inverse times B. So here I just assume that B is a normalized vector. But even if B is normalized, A inverse times B is not necessarily normalized, so it can be something large. So basically I have to do a renormalization, and then my goal is just try to encode the solution in the amplitude in a quantum state, which I just write is something like this, the cat x. So this is our setup. And of course, you can definitely ask, so whether this is a reasonable setup or not, or can we really extract some classical useful information from this quantum state? And I should say that is kind of a tricky issue, because in many literatures, so they just start from a quantum state and then output a quantum state, and they just call this the quantum linear system solver. But I should mention that post-selection might be expensive, so it might destroy some nice scaling that we will see later. But for simplicity, I will just assume this setup, and then also I will assume that the matrix, the spectral norm of A is equal to 1. So I have already renormalized my matrix, and I will assume some black box access to the matrix A and B. So we discussed this yesterday. Literally, I will just assume I will just assume a block encoding to A, and I will just assume a state preparation oracle to B. And then we look at this problem, and then we will discuss the complexity of solving this quantum linear system problem, and the complexity in terms of several important parameters. So the parameters that we will care about. So of course, we will care about the dimension, but I will not mention the dimension dependence explicitly, because it is naturally just something polylog in terms of this capital N. And there are two other parameters which we will discuss in a more explicit form. So one parameter is the tolerant error level epsilon. That is, we want this state cannot be really prepared. Exactly, we have to have some approximation. So error is the error that we have in the quantum state in the sense of vector 2 norm. And another important parameter is the condition number. So the condition number here is defined to be spectral norm of A times spectral norm of A inverse. So it is kind of describing the distance between the linear system and a singular system. That is, if the condition number is very large, then the matrix is close to a singular matrix, which means that the linear system is hard to solve. Okay, so this is our setup. And let's start with our first algorithm. And actually, this is also like the first quantum algorithm for solving linear system, which is the HHL algorithm. So the HHL algorithm is like the idea is very simple. So it is literally just computing this equation. So this is like the K equation in the HHL algorithm. That is, so if we assume that for my matrix A, remember that I'm assuming that it is a Hermitian matrix, so I can just like write down the eigenvector decomposition of this matrix A. That is, I have lambda j to be the eigenvalues, vj to be the eigenvectors or the normalized eigenvectors, and then like or just have, and then like I write down my right-hand side B to be expanded in terms of this eigenvectors, because like those eigenvectors form a orthogonal basis of your Hilbert space. And then like I can write down this and the corresponding like amplitude, where I just write down this to be beta j. And then we can just directly write down the solution of my linear system, the unnormalized solution. It is A inverse times B. So like A inverse has the spectral decomposition, something like this, because I just like change the eigenvalue to be lambda j inverse, and then like I'm acting this operator on my B, and what you can see that if you just like expand these brackets and those vj, so those I will have some vj prime, I will have some vj, so they become 0 when like j is not equal to j prime, but they are equal to 1 if j and j prime are equal. So basically like we will end up with something like this. So which means that so if we just change the basis to the eigenstates of the matrix A, and then what we are doing is that we are just like multiplying a lambda j inverse on the corresponding eigenstate. So this is the key equation, and then like the HHL algorithm is exactly trying to implement this equation. And let's see, so what do we need to implement this equation? So of course, because like here we only need to compute this lambda inverse. So we need like two subroutines or two like operations. So first, we need to get the information of lambda, right? So that is, if we are given an eigenstate Vj, and we need to know some information of lambda j using some quantum subroutine efficiently. So do you still remember what this kind of stuff is? I think like you heard that yesterday from Yu's tutorial, right? It is exactly the phase estimation algorithm or some kind of like eigenvalue problem. So the next operation is that after we get the information of this lambda j, then we need to like do this. We need to like multiply this factor lambda j inverse in the amplitude, and then this can be done by a single qubit rotation called the control rotation. I will just discuss this later. So have all the subroutines, and then okay, let me just be a little bit more specific. So like to get the eigenvalues of the eigenvalue information, then what we need is exactly the quantum phase estimation. So that is another reason that I really love the organization of this entire tutorial, because like Yu has already covered that a lot of stuff on the quantum phase estimation, which makes me easier to like discuss this HHL algorithm. But like here, I just write down the definition of the quantum phase estimation, but it is the ideal version, because like think like in the actual quantum phase estimation, you will have some probability distribution, have some superposition, but here I just only assume that we have an ideal phase estimation algorithm. So basically, it's just a unitary. It's a unitary operator, and if we have a psi to be the eigenvalue of to be the eigenstate of a unitary, and theta is the corresponding phase or like corresponding like eigenvalues of the Hamiltonian, then like what we can do is that we can just encode the binary representation of this theta in another register. So this is like the ideal phase estimation algorithm. And after we get this information, then like a second operation is the so-called the control rotation. That is like it is a single qubit rotation. That is, we have a 0, which is a single qubit, and then what we are doing is that we will like create a superposition between 0 and 1, and the amplitude of this 0 will be a function of theta. Of course, this function should be bounded by 1. So basically, like this is a general control rotation, a control rotation operation. So it can be like implemented. So of course, like there's some like detailed implementation for this circuit. So for this single gate, that is like probably like we need some binary representation of theta, and then like we first need to like binary encode the information of f theta and then perform the control rotation according to its binary representation. But like just trust me that we have some efficient way to implement this control rotation operation. Okay, now we have all the subroutines. And then the HHL algorithm is,
So this one, actually, there are two steps in the last thing, right? So one is f theta equal to cosine theta. The other is to compute arc cosine.
Yeah, that's right. Yeah.
First step is implemented very efficiently. The second step requires a classical arithmetic.
Classical arithmetic.
It's actually very expensive.
Yeah, that's right. But it's asymptotically still like expensive.
Yeah. Compared to some of the other solvers,
that's right.
Really a very major.
Yeah, that's right. Yeah, that's right. We have to use like for the general F, we have to use classical arithmetic, of course. Yeah.
You mean classical arithmetic on the quantum computer? Or?
On the quantum computer. Because once you do the phase estimation, you need to do the arc cosine in a coherent way to compute the phase envelope, and then you do the control rotation. That's a really, really expensive step if you want to implement that.
And the control rotation, the role is to come up with a unitary matrix?
Yeah, it is like a rotation, so it should be like unitary. That is like we need to have this orthogonal part 1 right there. Yeah.
In full generality, if you allow all functions f, that would be a large class of unitaries, right? Isn't that even a little bit too much to assume that you can implement that easy, right? I mean, because up to some very large probability, you can recover every classical function. And I heard there are quite a number of them.
Yeah, that's right. So here, like actually, like to really like, yeah, that's right. And just as Lin mentioned, so actually, if we want to like really implement this kind of circuit, it can be expensive in practice. But like here, also like if we want to translate a classical arithmetic to a quantum circuit, we also need some kind of like efficient algorithm for F. And here, the point is that we are only doing some kind of scalar valued function. So like there's like no dimension dependence. If we only care about the dimension dependence or the symptotic scaling in terms of the dimension, then this still should be fine. But of course, like in practice, so if the function is complicated, then this is definitely very complicated.
Yeah, but your theta could be 2 to the n, right? I mean,
Yeah, that's right. Yeah.
It could be large dimensions.
Yeah, it could be. Yeah, it is possible. Yeah, yeah, that's possible. Yeah.
So what's the second step to do arc cosine? So you just implement it like classically and then make it reversible?
Yeah, that's right. Yeah.
What is the depth? Like log or linear?
The depth will be, you will have some like poly factor in terms of the number of the qubits that you are using, if I remember that correctly.
It's a poly M, but the important thing is M is the number of digits, which has nothing to do with the system dimension, which is n, right? So also if you go from the classical and directly make it reversible, like through AND and XOR, I mean, that's a theoretical way to do it. Nobody would implement that in practice. In practice, if you really want to implement this arc cosine, you probably want to design special circuits.
Do you obtain any dependence of M on the system size when you have to calculate? I think, don't you need to end up rescaling the accuracy by the norm of the matrix? And so does that M, the number of digits of precision in theta, depend on that as well?
Yeah, that's right. It indeed depends on that, but like the M will only have a log dependence because here we have a binary representation, right? It's kind of like log 2 to the your whatever, or capital N or the spectral norm of H. So we will only have some log factors there. Yeah. Okay, yeah, great. Okay, yeah, let's go to the HHL algorithm. So like, yeah, the HHL algorithm is basically like I just discussed in the previous slides about that K equation. So we will first use the phase estimation to encode the information of the eigenvalues and then like do the control rotation to multiply 1 over lambda on the amplitude and then like do an inverse like phase estimation circuit to uncompute the auxiliary register. So basically like the circuit looks like this. And I will walk through the circuit to make sure that we can understand this algorithm. So basically like first we will start with 0, 0, B, where I just decompose this B in this like eigenbasis, and then in the eigenbasis of A. So here a remark is that we never do this decomposition explicitly. So this is like directly given. That is, if we have a B, then we can just directly write down this kind of thing. But we never really compute all of Bj or Vj explicitly. So this is just like a math notation. Like after that, we will do the phase estimation. But here, like the phase estimation is for the matrix. It is for the unitary e to the power 2 pi I times a, because like here, the phase estimation is for a unitary matrix, so we just want to consider this Hamiltonian simulation of the matrix A, and you can see that. So here, like the eigenvalues of A will serve as the phase factor in this unitary. So after the quantum phase estimation or ideal phase estimation, like we will have something in the second register to encode my desired eigenvalue. And here, this procedure is coherent. That is, because like in the first step, we are having a superposition of the different eigenvectors or the eigenstates. So when we apply this phase estimation on this superposition state, then actually we are kind of like coherently applying my phase estimation on like different eigenstates. And then like for different eigenstates, we will get like different corresponding eigenvalues. So basically like here we have like each lambda j for the corresponding like Vj eigenstate. And then after that, now we have the information of these eigenvalues, so we will do the control rotation, and the rotation is performed on the first ancillar qubit. And what we will have is something like this. So here, like the function that I'm choosing is exactly something like 1 over lambda j, but you know that this function is not bounded by 1. Actually, it is larger than 1 because like I have already rescaled my matrix to be from -1 to 1. So basically, like all these eigenvalues are from -1 to 1, and then like I have to like do some rescaling. I have like to add another rescaling factor c to make this function sin over lambda j to be like smaller than 1 for all the possible eigenvalues. So basically, like this c can be something like 1 over kappa because like the eigenvalue with the smallest absolute value is just something like 1 over kappa. And then have this kind of like rotation. So after the rotation, what I get is some state like this. And here, actually, you can see that. So now we've already have something that is very similar to the desired final solution that we want. So we have some beta j over lambda j times something Vj. So a superposition of everything like that. So the last step is we just do the uncompute. So like this uncompute is something that is like very common in designing quantum algorithms. So basically, like the uncomputing stuff is we just want to like reset the value in the ancillar register that we use in our previous algorithm. So by resetting the ancillar to be 0, then we can just like reuse that computational resource in later algorithms. So if you have any, but like this is kind of like a quite standard technique. Then we just like do the inverse of the quantum phase estimation, which is actually like we are just like resetting this lambda j to be 0. And then this is the final state that we get before measurement. And okay, here you can see that. Now in the ancillar qubit, so if we have 0, then the remaining part will be a rescaled solution of my linear system problem. And then the last step is to do the measurement in the ancillar qubit. And then if we get a 0, then we get the remaining part would be the normalized solution, the solution to the quantum linear system problem. Yeah.
So if this circuit was an input into another circuit, will you still have that uncomputation?
It would be beneficial because if you have, let's imagine, so if you have this uncomputation, then actually at the last step, you will have 0 in the second ancillar register, right? And then like you can reuse this ancillar register for example, like if you have a second algorithm, you will also need some kind of ancillar qubits, and then you can reuse the second register right here. So you don't.
Very expensive, but just to get that 0 all over again, you have to basically compute the inverse of that QPE. And
I think that has the same cost as the quantum phase estimation circuit, right? Because anyway, we just used it. Yeah, that's right. Yeah. I think that is still desired because like you just like repeat your work again, but like here, like the benefit is that you really save some computational resources, right? That can be like something which is quite expensive, right? But like it is kind of like a trade-off, right? Because if you have some more space resource, then probably you can just ignore this on computation step. Just want to make your circuit depths to be lower. So that is kind of like a trade-off. But I think like in the
here you have to do uncomputation.
Oh yeah. Here we have to do a computation because like we still have some lambda j the lambda j information in the second register. So if you just directly measure the 0, actually you don't get the final solution. Yeah, here we have to do that. But like in other algorithms, so it probably really depends on like your goal.
Yeah, here. So in this algorithm, your final output will actually be a normalized solution. Then, is there any way to get its normalization constant so that we can recover the exact solution?
Yeah, it is possible. Like it can be obtained by the amplitude estimation, right? Because like here we have some like measurement, and then like this measurement has some probability, right? And then like you can just like try to estimate the probability. Will give you the. Oh, C, you can just choose it at your own, yeah, on your own. So it's just C, just like you can just fix this to be, let's say, 1/2 kappa or something like that. Yeah, and then like this is actually something like it is actually, if you ignore this factor C, then the remaining part is exactly the unnormalized solution, which means that the probability of success will be like will be related to the actual norm of your solution. Right? Yeah.
I got a little confused. So what is the lambda j inside like the ket notation?
Oh, it is a binary representation. That is, for example, the lambda j you can write down is at something like yeah, you can write down your lambda j as something like 0 point, maybe let's say theta 0, theta 1, theta 2, blah, blah, blah. It's a binary representation.
So does that mean it's going to take multiple physical qubits?
Yeah, multiple physical qubits. That's right. Yeah. Yeah.
I have one very dumb question, but which always confuses me. So if you go to a physicist and show him this picture, he will say, okay, we are applying a circuit, right? A unitary transformation. And then if you go to your computation and you do what you just said, right? I mean, you're doing this amplitude estimation, the outcome is actually not a unitary operation, right? So sometimes if you look at the picture and then look at the mathematical problem, there's a little of grumbling in your stomach because you don't really know whether that is, what is defined to be a solution can be confusing, right? I mean, from a very systematic point of view. I don't know whether you have encountered that, but it always bothered me a little bit, right?
Yeah, I would kind of agree with that, but like I just feel, but like if you just ignore the measurement or post-selection part, so the circuit should be fine, right? It's like if I just write down everything, they are just perfect unitary operations, right?
Yeah, but if you ask what kind of problem can we solve?
Okay, yeah, that is another.
That's a different, right? So this measurement at the end is not as innocent as it looks like.
That's right. Yeah, exactly. That's right. Or if only for this measurement, it's okay because you are measuring on the computational basis. But like for other type of measurement, if you want to get some kind of expectation value, then it really depends.
I guess maybe Marius means that in the end, if we measure, we come with a success probability. So all these algorithms, if the underlying problem is not a unitary, in the end, we will have an algorithm that we have a procedure and this together with the success probability. We also want to make sure the success probability is fairly high.
That's true, but if you talk to physicists, they ignore all success probabilities 99% of the time, at least in what I mentioned. And then this becomes very strange.
What is 99%? Sorry? What is 99%? What is 99%?
Oh, I mean, if you talk to experimentalists, they often ignore these factors, the normalization factor, when they write something down.
Okay.
I mean, they should occur in the success probability of the experiment, but if often they write down non-normalized vectors without any hesitation. That's my experience. Anyway, that's
maybe we can postpone this discussion.
That's a very interesting discussion, right?
This is an interesting point, right? Because the success probability is depend on the condition number, which is like very big, could be, right? So
that's right. Yeah, I will just because you have to like if your condition number is large, then you have to like repeat for many times, and then I will just count the complexity later. Yeah, that's true.
But you mentioned earlier that the condition number is big is when we really care about these problems. This is hard to solve, right?
If the condition number is large, then it is really hard to solve. And actually, like this is kind of like the intrinsic difficulty for quantum algorithm. Like actually, we have some lower bound, which is saying that if the condition number is
classically is not.
Classically, it depends. Like, classically roughly we have two types of the the classical algorithm. So one is the direct algorithm based on some factorization, like you just do some Gaussian elimination, some like factorization, then that will only have a dimension dependence. But if you consider the iterative method, right, the convergence rate of the iterative method will still depend on the condition number.
So you're absolutely correct to observe that the success probability depends on kappa, and therefore you need a very large number of iterations if kappa is large. That's precisely the reason why HHL does not achieve the optimal scale.
Yeah, that's right. Yeah, that is what I'm going to talk about next. That is like the complexity estimate for HHL. It's a very rough complexity estimate. So like the complexity of the HHL, actually we have two sources of the complexity. That is, so first, for the single run of this circuit, we have some like complexity. And then we need to run this circuit for multiple times until a success. So we need many number of repeats. And then like for the single run, so the cost will be kappa over epsilon. I think you should have already known this like from the complexity of the phase estimation, because like for the quantum phase estimation, we have a scaling like something like 1 over epsilon. So here I'm ignoring some log factor. But like here the kappa scaling is really due to the multiplicative error requirement. That is, we want our eigenvalue to be estimated up to some multiplicative error, not the additive error. So we want the error to be something like epsilon over kappa, which means that it translates to the overall complexity to be something like kappa over epsilon. So this is like the first source of the complexity. The second is just like the number of the repeats. That is like we have some success probability, or we have some kind of like requirement for the repeats even after the amplitude amplification, and it definitely, like in the worst case, it will depend linear in terms of the condition number, which means that if the condition number is large, you have to like do many times of the iterations. And then the overall complexity will be like, will be something like kappa square over epsilon, which means that, so now we have a kappa square dependence, have a 1 over epsilon dependence. So if you really want to compare with your classical algorithm, you can say that they are not quite favorable scaling, because like in classical algorithm, for example, if we want to use the conjugate gradient for positive definite matrix, then we only have a square root of kappa there. And also like the conjugate gradient method have a log 1 over epsilon dependence. But here like we have a kappa square over epsilon, so the advantage is really on the dimension that we didn't specify here. So this is like the overall complexity for the HHL. We have kappa square over epsilon, and then after this first quantum algorithm, so like people were not very satisfied of this complexity. So we always want to like improve this complexity dependence in both kappa and epsilon. So like here I will just like present two possible methods of improving this kappa and epsilon dependence. So the first,
Yeah. So here, when you measure the error, what kind of norm you use?
The vector 2 norm.
Vector 2 norm.
Yeah.
It's very silly. I mean, if you give me access to e to the 2 pi I a t, which is what you use in this quantum basis estimation, if you were to just integrate it from 0 to t, you get 1 over a times e to the 2 pi I t, right? So you get the inverse of a. So that's some linear combination of unitaries and all of that, so you can do that. Is that worse than this algorithm? Or?
That is actually better. It's my next algorithm. Yeah. yeah, thanks for the connection. It's really nice. Yes. So next introduction, actually, the next algorithm is exactly the LCU algorithm. So the LCU is the name of the quantum subroutine that we will use in this method. So here's like a very quick review of what we had yesterday on the LCU. That is, we can implement the linear combination of unitaries. So we have a prepare oracle, have a select oracle. Then like we also need some measurement, and then like the number of repeats will depends on like the one norm of the coefficients. And of course, we need some kind of like we also need to analyze the cost of implementing this select oracle. And then the idea for the LCU method for linear system is exactly we want to decompose this matrix function A inverse as a linear combination of unitaries. Maybe something like e to the 2 pi IA or something else. Like the first approach is the Fourier approach. That is, we will exactly use something that is the Hamiltonian simulation of the matrix A. So like here is kind of like the detailed representation, but there are just some math equations. I will just like try to work through them quickly. That is, we start with the first identity. That is, 1 over x can be written down as the double integral like this, and you can check that. So it is not very hard to compute. And then like after this equation, then we will just like, the left-hand side, we replace this x by a. So remember that here we have a Hermitian matrix A. So basically, like the matrix function is defined on its eigenvalues that we are just doing some eigenvalue transformation. So the A inverse can be something on the right, which is I just replace this x here by my matrix A. And then if we look at this integral formula, then it is just like a continuous linear combination of the unitary, right? And then like, if we want to really numerically implement this, then what we will do is that we just do some like truncation, some numerical quadrature, some discretization. Then after that, we get a formula in terms of the linear combination of unitaries. So this is the key formula. And then the quantum algorithm, I will not write down the circuit for that, but it is exactly the same as the general linear combination of unitary circuits. Okay, so like to implement this, of course, like, and like go back to the question, so whether this is better than the HHL or not. So actually this is better. So the reason is that it is better in terms of the epsilon dependence, because like here we are using some kind of like something similar to the Fourier expansion. You can expect that. So it will have some kind of nice decaying property and some nice convergence results. So basically like if you just like do the analyze carefully, you can find out that. So here the truncation order for those infinite integral can be something like polylog in terms of 1 over epsilon. And then it will translate into the complexity of my final algorithm to be something like polylog 1 over epsilon. So this is like a better algorithm compared to HHL. Yeah.
Sorry, is there like why do we get this, like, I guess this is an exponential convergence rate? Like, why do we get that in this setting? Because like A inverse should have like,
oh yeah, it is really because like this A inverse is, it is kind of like bounded away from the origin. Because like we assume that the eigenvalue of A is kind of like in the regime of -1 to -1 over kappa plus 1 over kappa to 1. So it is bounded away from 0. So it has some nice convergence. And here you can see that the truncation order have some not very good dependence in terms of kappa. It's really because like we get closer to the original, then we'll have some like worse result. Yeah, oh, have like many questions. So yeah, start.
Okay, so, sorry, I just kind of didn't understand totally. Like, what are these x, y's, and z's here? Like, I didn't totally understand this composition.
Oh, sorry, they are not the gate. They are just like some scalar, some variables.
So, like, how do we know what they are? Like, how do we decompose this? Like, you know, the large z, like the large y. Like, how do we get?
Oh. Here it's like, it's kind of like the super parameter that you can choose before your algorithm. But like if you just want to like control all the approximation by some like desired error, then you should like choose y or z to be some parameter like this. Right?
Oh, so we choose this beforehand.
Yeah, that's
okay,
right.
And then we sum over like all the like possible. Okay.
Yeah, that's right. Yeah.
This is purely designed in quadrature, as you say.
Yeah.
So if there is explicit choice, it's just writing this down.
This is so.
It's purely a quadrature thing.
Okay.
When you have a one-dimensional integral, you want to design a quadrature. It's good.
Okay.
Yeah.
I'm confused about the conclusion that this is a better algorithm. Doesn't it have a worse dependence on kappa?
Oh, so the dependence on kappa it is still like kappa squared, and I'm ignoring the polylog factor because like the polylog is usually like much smaller compared to the poly dependence, right? Yeah. Yeah, and also I should mention that in the HHL we also have some polylog kappa. I just like didn't really write down that explicitly.
Oh, okay.
Yeah.
Although the overall complexity is correct, but I realized it uses something that nobody has talked about so far, which is the Grover speedup.
That's right. Yeah.
Right? So to get kappa square scaling, you have already used amplitude amplification.
That's right. Yeah.
Don't use that as kappa cube.
Yeah, it's kappa cube. That's right. Yeah. Yeah, but I will try to talk about the amplitude amplification at the end of the talk. Yeah.
So you said that I think someone back there asked about how it's better with the kappa, and you said like that A was being approximated away from the original.
Yeah, that's right.
So if the original A has a high condition number, it's desirable to decompose it into unitaries that make the kappa better.
You cannot make the kappa better, right? Because like the distance between the desired interval and the region it is determined by the condition number, right? Because like here I have rescaled my matrix to have the spectral norm 1, and then like the smallest eigenvalue, the eigenvalue with the smallest absolute value would be something like 1 over kappa, right? So of course, if kappa is very large, then it will close to a region, and then the problem will be harder to solve. And actually, like on quantum devices, so if kappa is very, very large, then no quantum algorithm can be efficient generically.
But then how do you approximate it away from the kappa?
We just kind of use the same formula, but we have to choose this truncation order to be higher if you're, yeah. Yeah, that's right, because like the original identity, it is true for all x, which is not equal to 0. So like the effect of this condition number will only affect the truncation order right here. So if your kappa is larger, then you just have to choose a large truncation order, and it will result in like more expensive complexity.
Maybe it's worth pointing out that once you plug A into the algorithm, into this formula, you effectively constrain X to be inside the spectrum of A.
That's right.
So therefore, the moment X is away from 0, then that identity somehow is happier, and so you can numerically better approximate the integrals.
Yeah.
I have a, if I may, right? So assume again that we have small eigenvalues, and you can't help it because your problem has them.
That's right.
Can you find an algorithm which gives you a solution ignoring them, somehow calculating pseudo-inverse for the large kappa, and it just is not accurate, but is running faster?
Oh, that's a great point. So I try to answer this question from two perspectives. So if we want a generic quantum algorithm, that is, if we are very ambitious, that is, we want an algorithm which can solve all the linear system problem, then the answer is no. We cannot go faster than the linear dependency in terms of the condition number. However, in practice, we are not always that ambitious. We only care about some system with special structure, right? So if for a subset of the linear system, then the answer is yes. So it is called the fast-forwardable quantum algorithm. That is like for example, if you imagine like a diagonal matrix, then that is like much easier, right? Yeah. So for specific system, it is possible.
Possible to project out all the small
Sorry.
Oh, possible to project out.
Yeah, it is possible to have some like complexity which is even independent of the condition number. Yeah, for some specific system, of course. Yeah.
Is it possible to get a quadratic dependence on kappa in the case where A is positive definite?
Oh, that's a this algorithm also works for positive definite case, right? So you're asking whether we can get better scaling, right?
Yeah, I guess it's like with conjugate gradient, if you have positive definite, you get like a quadratic kappa dependence.
Oh, sorry.
Or square root kappa.
Okay.
Sorry. Yeah.
Oh, yeah.
So I was wondering if I think you mentioned that kappa was kind of the lower bound one would expect.
Yeah, that's right. And that is also true for the Hermitian positive definite case. We mean that on the quantum devices, you cannot get square root of kappa even for positive definite matrix. But if you have some further assumption, you can somehow get that. So, yeah.
I'm sorry, if we could go back to the HHL, could you go back to the side where you defined the quantum phase estimation?
Yeah, sure. It's, I guess it's right here, yeah.
Okay, so you take the ancilla register 0, and then you encode some binary encoding theta into there. But that's so you have one psi, and for that psi, you take the register to one scalar. But then in the HHL algorithm, you have like a eigenbasis, and you take each eigenvector, you do a different register, or like you do a different value for each one.
Yeah, it's kind of like done like coherently or automatically or in parallel. So it's kind of like because we have the superposition automatically, and then if you just directly apply your phase estimation, then for each eigenstate, it will just like correspondingly encode your like desired eigenvalue for different eigenstates, right?
So then does theta then depend on psi?
Yeah, that's right. Yeah.
Okay.
Another question? Let me go back to the slides for the LCU.
Yeah, so the scheme mainly depends on the key identity. I was wondering, like, is there any other identity you may want to use to develop some scheme like this? Maybe have better convergence rate?
That is in my next slide. Yeah, we get very great question. Yeah.
So to run the algorithm, do you need to have some prior knowledge about the matrix? For example, do you need to know some bound on the contact number? What if you don't know the contact number? How do you run this LCU approach?
We cannot run that. We need some upper bound of the condition number. Okay, great. So I realized that I'm heavily behind my schedule, but I will just try to cover the most important materials that I wanna discuss, and also please feel free to ask me questions. Yeah, I love questions. I love discussions. And then the next approach of LCU, since I just promised, I will just go it very quickly. That is another way of expanding this function when
maybe since you're exactly half of it, right? And maybe what we can do is not rush.
Okay.
But since you won't be here until workshop 1, is that right?
I think so, yeah.
Yeah, so...
sorry, it's not until workshop 1, it's just this week.
Okay, yeah, you're going to stay here, but then you're going to be gone. You're going to come back in workshop 1. But during this 2 weeks or so in between, I mean, you can upload the slides to the page, and so people can look at that. But also, if there's interest from the audience during the off-workshop weeks, maybe you can give a Zoom talk here in this room sometime.
No problem, yeah. Yeah, sure, yeah, no problem. Okay, yeah, no problem, yeah.
That's a very good idea.
Okay, great. Okay, then let me continue with this LCU approach. That is the second approach is really based on some polynomial expansion, another polynomial expansion. That is we're using the Chebyshev polynomial expansion, because we know that if we want to approximate some general function, then the Chebyshev polynomial is maybe one of the best solutions that we want, because it has some nice structure in doing interpolation, and also it is close to the best polynomial approximation in the min-max sense. So basically the Chebyshev polynomial is defined as this. So if you're not familiar with that, it's basically it's kind of it is easier to start with this kind of iterative relation that you start with the zero order Chebyshev polynomial is 1, first order is x, and then you can use this iterative relation to recursive relation to kind of define your high order Chebyshev polynomial. And there's another consensus representation of the Chebyshev polynomial. If you just write down your variable to be something like cosine theta, and then it's just kind of cosine of n theta for nth order Chebyshev polynomial. Okay, so the Chebyshev polynomial is bounded by 1 on the interval -1 to 1, and then the approach of solving linear system is kind of we are trying to approximate this function using the Chebyshev polynomial as the basis functions. And then the idea is that, so we first kind of make this function to be well defined on the entire interval of -1 to 1. That is we will add another term, which is something like 1 minus x squared to the power d, where d is kind of another parameter. So here you can see that. So it is not a good approximation when x is close to 0. So it is a good approximation when x is away from 0, and this d will help you to control the performance of your approximation, which means that this d will actually, it will depend on the condition numbers. You can see that. So here, this d, if we want this approximation to be an absolute approximation on the interval, let's say 1 over kappa to 1, and then we have to choose d to be something like kappa square or something like that. Of course, for epsilon, it is still very good. So we have this kind of approximation, and then the next computations, they are just doing some the second line is just a Chebyshev polynomial expansion. That is because this function is already a polynomial, right? So we just write it down as the basis of the Chebyshev polynomial. So we have something like this. It is a good exercise to really check the correctness of this equation. And after that, what we will do is that we will further truncate this kind of polynomial. So although this is a polynomial, but the degree of this polynomial is very high, because here you can see that, so here d is something like kappa squared. So and remember that, so this d will come into the complexity in the LCU algorithm, but we still have some other parameter due to the number of the repeats of my LCU circuit. So the complexity will be worse than kappa squared if we directly use the polynomial in the second line. So like to get better scaling, what we will do is that we will further truncate this polynomial because like for the high order Chebyshev polynomial, so they have very small coefficients. So you can just try to like analyze that rigorously. And then like what we will get is that we will get another polynomial, and then this polynomial is only up to some order capital J. And this J can be chosen to be something like square root of D, which means that this J is just like something like linear in terms of the condition number. So this is like another way of approximate my function 1 over x. And then to implement this, we need the LCU, but the question is that here it is not directly,
Yeah, so in your last approximation, why is this J independent of kappa?
Oh, it is still dependent on kappa because here we have a D, and D will be something like.
Oh yeah. So then my question is, if you consider the error of this approximation like in the L infinity norm, it's still not not a good approximation. You still need your x to be larger than kappa to make this to be a good approximation.
That's right. X should be larger than 1 over kappa. Yeah, that's right.
Sorry, the first approximation is error epsilon approximation. What's the last one? Is that still?
It is again the error approximation in terms of the infinity norm. Yeah. Okay, great. Yeah, we have this approximation, and we want to like implement this. We will use LCU, but the question is that so here we have a Chebyshev polynomial. If we replace this x by a, we have a Chebyshev polynomial of a, which is not a unitary operator. So what we should do is that, so basically like what we should do is that we should like, again use LCU, but it's the linear combination of block encodings. That is, we need to really construct the block encodings of the Chebyshev polynomials. And then after that, we can use the LCU to like really like implement this approach. And the construction of the the construction of the block encoding of Chebyshev polynomials is another important task, which I was planning to discuss in the cubitization session, but probably I will not cover that today. But like, you can try to think of this on your own, but like it is a very difficult task. I will just like maybe discuss this if you have chance, like maybe like in several. Yeah.
Can I come back to my previous question?
Okay. Yeah.
So you want to calculate this inverse, right? Now you have a bad condition number, but I guarantee you that I will only use the large eigenvalues. Will this algorithm still work?
It still works, and it is better. It has better complexity. It will depend on your something like your effective condition number.
Yeah. So if I have a guarantee that I'm not using the bad eigenvalues, I can still use it.
You can still use that.
And I will still get a good result. I just have to make that guarantee happen.
Yeah, you have to make that guarantee happen, and you need to know that you need to know your effective condition number, right? You need to like really because
sure.
You can still use the algorithm, and you will get better.
The effective number of the pseudo inverse restricted to the spectrum.
Yeah, that's right. Yeah, that's right.
Good.
Yeah. Okay, great. Yeah, that is for the LCU approach. That is okay. So the overall complexity, you can see that is like we have some exponential improvement in terms of the precision, but we still have some like kappa squared dependence in terms of the condition number. And then the next question is that can we further improve this kappa squared dependence in the quantum linear system algorithm? And I was just going to present you like a third algorithm which can achieve linear dependence in terms of the condition number without any complicated subroutine. So the algorithm that we will use is based on a different framework. It is called the adiabatic quantum computing. So I just want to like introduce as a very general framework for the eigenvalue problems. So I just want to start with the general setup of the adiabatic quantum computing. So the adiabatic quantum computing is that we are considering a time-dependent Schrodinger equation. So here H is a time-dependent Hermitian matrix, or it's just like a Hamiltonian. And then we are considering this Schrodinger equation. And here we have some feature for this Hamiltonian H. So first, this h is changing very slowly because like here you can see that so the argument of this h is something like little t over capital T, which means that it is changing on the level of a rescaled time, right? It's like if my physical evolution time capital T is very large, then actually like my Hamiltonian is changing quite slowly. And the second feature is that I will assume that this Hamiltonian had some gap condition. So the gap condition means that one of the eigenpath of my Hamiltonian is kind of like separated from the rest of the spectrum. So like here, just on the right, I just draw like a figure from a toy example from the like 4-level system. So basically like x-axis is the rescale time, little t over capital T, and the y-axis is the eigenvalues of my Hamiltonian h of, this should be t over capital T, but like it is is the Hamiltonian of it is the eigenvalues of my Hamiltonian. So if we look at this path, the ground energy path, so it is kind of like bounded away from the rest of the spectrum by some kind of gap. So I would say that this spectral path, it satisfies the gap condition. And also if you look at this path, it also satisfies the gap condition. But for the second and the third in the middle, so they have some crossing, they are like very close, so they don't really have a gap, they don't satisfy the gap condition. And now I have this assumption. I'm assuming that h is very slow. I'm assuming that I have some gap condition, and then the adiabatic quantum computing is based on the adiabatic evolution, saying that. So if the initial condition of my Schrodinger equation is an eigenstate corresponding to the eigenpath which satisfies the gap condition, and then the Schrodinger equation will approximately drive my dynamics along that eigenpath. That is, for example, if I start with the eigenvector corresponding to this 0 eigenvalue, then I solve this Schrodinger equation, and then my final solution will be approximately the eigenstate right here, which I'm just following this eigenpath. And of course, if I start with the eigenvector here, and then I will approximately following this eigenpath. So this is the most important phenomenon, like the underlying phenomenon of the adiabatic quantum computing. And here you can immediately see that. So this is kind of like a framework on quantum devices for solving eigenvalue problem, right? Because like on quantum devices, we are expecting that we have some efficient quantum algorithm for simulating this Schrodinger equation by Hamiltonian simulation. I think Dee talked about that yesterday for some time-independent algorithm, but like for the time-dependent algorithm, it is the same story. That is, we have some efficient quantum algorithm for digital simulation. And then we just kind of like translate a eigenvalue problem to the problem of Hamiltonian simulation, which means that we can somehow like efficiently solve the eigenvalue problems on a quantum device if using this adiabatic quantum computing if we have the gap condition. Okay, so this is like, I think this is kind of like a beautiful mathematical framework for like really kind of like relating the differential equation, the Hamiltonian simulation with the eigenvalue problem. Yeah.
So this is essentially very similar what we know like homotopy, how we solve the continuation of the eigenvalue problem. So I'm wondering, so you're making this assumption, it's very clear that you have a gap, so you have it well separated. But in the continuation homotopy methods, we have techniques like to trace like bifurcation points, or if you have the two eigenvalues that may be very close, but they're not really crossing. Is any of that, has anyone or people are looking on trying to transfer those techniques into this framework? Or?
Yeah, there are some like rigorous theorem on that. So it is kind of like called adiabatic theorem without a gap condition. So you will have some kind of like analyze on the probability of the transition, and also like even like it is kind of under some kind of smoothness condition, you can still like on the eigenpath even if you don't have a gap condition. Okay. Yeah, there are some works. Yeah.
But even if you have a gap, there's still a probability of.
That's right. Yeah, that's right.
Wouldn't you expect the gap to close exponentially with the amount of?
Yeah, if the gap is very small, then like we will have some larger error, because like here the final state will never be the exact eigenstate. It will only be an approximation, which means that you have some like transition rate, you have some transition outside your desired eigenspace. And then later in the next slide, I think I will just try, or I have a slide to bound the transition error, to bound the transition rate according to the gap. But like the short argument is that if the gap is small, then we will have some larger error. And then to reduce that larger error, we have to make this evolution time to be large, to slow down my Hamiltonian. Okay, yeah, great. So, okay, like this is like a framework for using differential equation to solve eigenvalue problems. And then like, remember that, so our goal is try to solve the linear system problem. So we still need to like formulate the quantum linear system problem as a eigenvalue problem, right? And then like, this can be done like straightforwardly by like constructing your Hamiltonian H0 and H1 to be something like this. So basically like, we will construct my Hamiltonian to be a linear interpolation between H0 and H1. So H0 is my initial Hamiltonian, H1 is my final Hamiltonian. And this H0 is something like 0 QB, QB0, which only depends on my right-hand side of my linear system. And QB is the projector onto a orthogonal basis, is spanned by B. And then like, so this H1 is the final Hamiltonian, and it has something, it looks like this. And then you can verify that. So these two Hamiltonians, they are quite simple Hamiltonians, and the blocking codings are efficiently constructible given the state preparation of B and the blocking coding of A, of course. So they are quite, it is not hard to really construct the blocking coding of these two matrices. And then it can do the desired thing. That is, for example, like for H1, you can check that my vector x0 is a eigenstate of this H1 corresponding to the 0 eigenvalue. So just like multiply this H1 on the vector x0, and then you can check that. So for H0, we have a very easy eigenstate, which is exactly B0, because like we assume that we know B. And then you can check that B0 is the eigenstate of H0 corresponding to the 0 eigenvalue. And the even better thing is that these two vectors, they are connected by an adiabatic path which is separated from the rest of the spectrum. So here, basically, like they are connected by this zero line, and then like for all the other spectrum, I'm ignoring some orthogonal space, but I just want to make things to be simple. So they are kind of like separated from the rest of the spectrum by some gap. So on the right is the eigenvalues of my linear interpolating Hamiltonian. So use this formalism, we translate our linear system problem to an eigenvalue problem, and then like we can directly apply the adiabatic quantum computing framework to solve this linear system problem. And then the next question is that, what is the computational cost, right? Because like we want some new algorithm to have better dependence in terms of the condition number, and also have some like log dependence in terms of the epsilon. But like, what is the complexity of this approach? And I should say that, so this naive implementation of the adiabatic quantum computing does not have a very nice scaling. So it is really because the gap at the end is very small. So you can show that the gap at the end is something like 1 over kappa, which means that we need to choose our evolution time to be very large. And I guess I have some rigorous theorem on that. So which is a rigorous theorem that bounds the adiabatic arrow. So basically, like here, so this eta s is the distance between the exact eigenstate and the solution of my Schrodinger equation. That is, I'm bounding the difference between these two vectors. And on the right, you can see it has some complicated representation, but like let me just try to show you some important parameters. So first, we have a parameter of t. And if you look at the scaling in t, it is something like 1 over t, which means that it is a linear convergence method. So we have a dependence on 1 over t. And if you look at the gap condition, that is, I'm assuming the gap to be denoted by this delta s for the Hamiltonian H of s, and then like it has, in the worst case, it has a inverse cubic dependence in terms of the gap. Okay, and then we use this error bound. And it turns out that, so I have shown you that, so the gap condition right here is something like 1 over kappa, but here we have some like delta cube dependence. So basically, like what we need to do is that we need to choose this capital T to be very large if we want to bound this arrow by some epsilon. So this capital T will be something like the gap cube inverse times like 1 over epsilon. And then remember that, so if we want to solve the corresponding Schrodinger equation, the Hamiltonian simulation problem, the cost will be linear in terms of this evolution time t. And then you can see that the overall scaling will be kappa cube over epsilon, which is even worse than the HHL algorithm, right? So this is like a naive implementation of the adiabatic approach. But like, fortunately, we have some way of improving this algorithm. So the way of improving this algorithm is that, so we just go back to look at this error formula. So you see that here we use this bound only in the worst case. That is, we just directly look at this single term. We have a delta cube. But like we also need to look at the numerator. That is, like on the numerator, we have a derivative of my Hamiltonian h, which means that when the gap is small, if I just slow down my Hamiltonian, that is, like if my gap is when the gap at the point when the gap is very small, I just like make this derivative of my Hamiltonian to be slower, then probably I can cancel some gap dependence, right? I can probably like get some better dependence in terms of the gap. And fortunately, in my system, so the gap is not always small, right? So we only have a small gap at the very end. So for example, for the first half of this propagation, so actually we have a quite large gap. So the gap is larger than 1/2. So it is like quite large. It means that at the first part or during the most part of my evolution, I can choose the derivative to be very large, which means that I can drive my system to be very fast. And then I only need to slow down at the end of my dynamics to cancel the kappa dependence brought it by this smallest gap. So, which means that in the previous slides, I just do a linear combination. This is like a constant speed interpolation. You cannot do that. But like what I'm going to do is that I'm going to consider like a new interpolation function. I just have a function f of s, which can have different speed at different time. And then like I just want to like choose this f to satisfy the property that I just discussed before. I want it to be very fast at the beginning and to be very slow at the end. So fortunately, we have a very nice choice of this gap, which is specified in this ordinary differential equation. I just choose the gap to satisfy this ODE, which is like the derivative of f is proportional to the power of the gap. And I should mention that. So in the linear system problem, so this ODE is explicitly solvable. You can write down the analytic expression of the solution of this kind of interpolation function. But if you want to like use this adiabatic framework for some general problem, and if you still want to get some gap dependence, you can still use this kind of like interpolation function. But for different problem, you will need the information of this gap at every time, which is a very big assumption for other problems. But here for the linear system, we are very lucky. So actually, we know that information. You can really like compute it on your scratching paper. Okay, and then we use that, and then it does the desired thing that we want, and you can show that the overall complexity can be reduced to be something like linear kappa over epsilon. So it is really because in the previous error bound, we have a square in the numerator, have a cube in the denominator, and then like the square canceled some 1 over some kappa square scaling, and we will get something like kappa over epsilon dependence, which is very nice in terms of kappa, right? Because like this is like a linear dependence in terms of the kappa. But we still have some bad thing. That is, we have a 1 over epsilon dependence in terms of the precision. So in terms of the precision, it is worse than the LCU approach. And then the next question is that, can we further improve this? Can we get a kappa dependence and a polylog dependence in 1 over epsilon simultaneously? And the answer is, again, it is a yes. And we can use a further improved version of the adiabatic quantum computing. So the further improved version is that, so let me go back to this. So this 1 over epsilon scaling dependence, so what is the source of this dependence? It is really because in my adiabatic theorem, I have a 1 over t dependence. So if I can improve this 1 over t dependence to be something like 1 over t to the high order polynomial, and then like I can somehow improve the epsilon dependence, right? And then like the goal is, so basically it is that I want to improve my adiabatic theorem or my adiabatic error bound to be something like 1 over t to the power k. And then this can be done by so-called the boundary cancellation condition. So I should say that this high order convergence in the adiabatic theorem, it does not hold in general. That is, if you just give me an interpolation function f of s, so the best scaling that you can get for general function is just 1 over k. But if my interpolation function satisfies some nice condition, then you can somehow like further reduce your error. So this condition is just called the boundary cancellation condition. So the boundary cancellation condition is defined to be that the support of my derivative of my Hamiltonian is within the open interval 0 to 1. So it really means that the derivative of h at any order is 0 at 0 and 1, which means that on the boundary, I have vanishing derivatives of any order. So it is like so you can see that this function is not a real analytic function, right? Because if it is a real analytic function, you can do a Taylor expansion. So if the high order derivatives, they are all 0, then you will just get a constant function, which cannot be an interpolation function. Like we have some nice function which is smooth, but not real analytic. I think you probably like learned that from your like analysis course, but like I will show you another example of this type of function. But if we have that function, we can improve the error. So I'm just showing you like how we try to improve that error. So it is like kind of like a conceptual proof of this high order adiabatic theorem. We just do this by integration by parts. Because if I go back to the error bound that I showed you before, so this is the first order error bound. And for this error bound, actually we have two parts. So the first part is that we have some boundary term, right? We have some kind of term evaluated at 0 and my final time s. So here I just only care about the error at s. So I have some boundary term, and I have some like integral term, and then like this formula is actually proved by the integration by parts formula. But like the good thing is that I will do the integration by parts formula again. That is, for this integral, I will use the integration by parts, and then what I'm getting is that I'm getting a second boundary term and another integral. But like when I do the integration by parts, I will get the extra scaling of 1 over t because like my Hamiltonian is changing very, very slowly. So I will just benefit this slow changing Hamiltonian, then I will just get a actual parameter of 1 over t. And then the strategy is that I will do this again and again. And then I will just like do the integration by parts again. I will have a third boundary condition. I will have 1 over t cubed. And then like under the boundary cancellation condition, so all the boundary terms, they are 0. And then what I will get is that I will just get a high order dependence in terms of 1 over t. So this is like why we can get a better dependence in terms of t if we have the boundary cancellation condition. And then with that, this is probably like the final slides for the adiabatic problem. Yeah.
Yeah, right. So in this explanation, you only need all the boundary term vanishes. Then
that's right.
Why you also need this h prime s or the support of h prime s?
Oh, it is kind of like an equivalent representation of the vanishing boundary, right? Yeah, if like the support is within the open interval 0 and 1, then you can just compute like the high order derivatives, they are 0 at the boundary. Okay, so like the next, the algorithm is just like we use this improved version of the adiabatic quantum computing. We have some improvement in terms of the dependence on 1 over t. And the function that I'm going to use is this function. So like this function is kind of like, you can see that it has an explicit representation like this, but like it is kind of called the glue function. So in analysis, it's kind of like used to like smoothly connect to like smooth functions. So basically like I have a very flat performance at the beginning and very flat at the end. And then you can see that so it satisfies the boundary cancellation condition. So it has a better dependence in terms of 1 over t. And then it also slows down at the end, which means that it can also cancel the gap dependence. Although I'm not showing that explicitly, but it can also cancel the gap dependence at the very end, which means that if you just plug this choice back into your error bound, then you can show that in order to bound the error by epsilon, this t is something like kappa polylog 1 over epsilon, which means that we achieve the linear dependence, almost linear dependence in terms of the condition number, and a polylog dependence in terms of 1 over epsilon simultaneously. Okay, yeah, I guess I have covered all the 3 algorithms for the linear system, but like I just want to like discuss a little bit more about like something beyond the generic algorithm. That is, so far we only care about the generic quantum algorithm. That is, we are very ambitious. We want to design an algorithm which can work for all the linear system. But like, as I just like mentioned earlier, that is, so if we only care about like a subset of the linear system, of course, we can somehow do better. And also like, if your linear system has a very large condition number, then all the previous algorithms, they are very expensive because they have polynomial dependence in terms of a condition number. So like classically, so when we have some L-conditioned system, so we usually use a preconditioner, right? That is like, we have another matrix M, and then instead of solving this original AX equals B, what we will solve is that we will solve this MAX equals MB, and we want this matrix MA to have a smaller condition number. And then this M is called the preconditioner, and then like on the quantum devices, you can do something similar. That is like we have some existing work on using the sparse approximation inverse, or using the circular matrix, or using the diagonal matrix. But I have to say that I will not go into details of these algorithms, but I have to say that I think this is a well-studied topic in quantum algorithm. That is, so I think because like in the classical literature, you probably know that there are many, many different preconditioners for different systems. But like for quantum algorithms, I think these are probably the only three, or I have to be like a little bit conservative. I think like the available quantum preconditioner might be less than 10. So it is kind of like, please correct me if you have like a different point of view, but I just feel like this might be something that we can really work on. That is like, we can try to really design some quantum preconditioner, but it is not a very easy task, because like, you know that on quantum devices, we have some restrictions on implementing all the matrices and this kind of matrix operations. So we still have to make sure that the corresponding like structure of the preconditioner is desirable for my quantum devices, for the implementation or for the block encoding for any like matrix operations. So this is like a little bit about the preconditioning. I think I have some details, but I will jump through to the summary. I guess it is also like a good point for me to stop here. It's like today I covered the quantum algorithms for solving linear systems. So we start with the HHL. So the HHL is based on the phase estimation and the Hamiltonian simulation subroutine. It's the first quantum algorithm. And the overall complexity is something like kappa squared over epsilon. For LCU, it is based on the polynomial approximation of your function 1 over x. And of course, you can imagine that the LCU is a very powerful tool. That is, if you have some arbitrary function f of x, if you have some nice polynomial approximation, then you can always try to implement that by your LCU approach. But we just need to be careful about the complexity due to the LCU circuit. So for the linear system, it's kappa squared, polylog 1 over epsilon. And for the adiabatic, it is based on like a different framework, which kind of like relating the differential equation with the eigenvalue problem and also the linear system problem. And then like it can be something like linear in terms of the condition number and polylog in terms of 1 over epsilon. And there are two things that I didn't mention in the talk. That is, so first, you may wondering that, so for adiabatic quantum computing, we have linear in kappa, we have polylog in 1 over epsilon. Then can we even do better? Can we do, for example, square root of kappa, or even something like log 1 over epsilon? And the answer, I think, like I already discussed that when addressing the questions. That is, the answer is no, because we have some quantum lower bound. That is, if you have a generic quantum algorithm, then you can never do better than linear in kappa times log 1 over epsilon. So this is the best thing you can expect. And the second thing that I didn't discuss is that, so all of the algorithms, I only show you the simplest version. So for all of these three algorithms, they have some further improvements which can like further improve their dependence. So for example, like for HHL, if you use a technique so-called the variable time amplitude amplification, it can be kind of like improved to linear in kappa, but you will have some worse dependence in the precision. And for the LCU, use the same technique, use the same variable time amplitude amplification. It can be improved to like linear in kappa and polylog 1 over epsilon. And for the adiabatic quantum computing, so we have a clever way to do the Hamiltonian simulation when the Hamiltonian is near adiabatic, and then the overall complexity is only kappa times log 1 over epsilon. So it is not polylog, and we don't even have a log factor in kappa in the overall adiabatic quantum computing. And here you can see that this improved version of the adiabatic has already matched the lower bound, which means that is why I'm thinking that maybe for generic quantum algorithms, so this problem has been solved. But like for the preconditioning system, there are still like a lot of works for us to do. And I guess this is the good point. And with that, I would like to conclude. And thank you for your attention.